Ready?
Yeah.
Okay. All right. So this is Demphus by Rosen, Diankov. The title is Automated Construction of Robotic Manipulation Programs. The committee consists of myself, Takeo Kanade, my co-chair, Professor James Kaffner. Also, as from outside, we have Professor Kei Okada from the University of Tokyo with Skype and telephone. And then Professor Paul Rubinstein from CMU Robotics. Okay.
All right.
Rosen, sorry. Could you connect the Skype again?
Yes, I just dialed you.
Okay.
Can you see me?
Yes.
Okay, excellent. All right, well, thank you everybody for being here. So during my time here at CMU, I've had the honor and a lot of pleasure working with many robot platforms and try to get manipulation working on them. And sort of this culminated in a lot of really cool algorithms to really automate a lot of the really tedious processes in automation in manipulation. And hopefully this will serve as a footstep for a lot of future manipulation research. If you look at the robots functioning in the world today, what you'll see is that most of them do repetitive tasks really well. And they're very efficient at it. However, the problem is that when something small changes, a team of engineers will have to get together and reprogram the task again. And this takes a lot of time, and it's a lot of design efforts. So some of the issues that we want to try to address here is how do you actually program these robots? How do you develop the algorithms in order to automate and make it much simpler for engineers to use these things and to develop mass production systems? So I want to begin with a small example here of mobile manipulation. And we have a problem specification here where the robot is a humanoid robot with 2 arms. There's a gripper, and then there's a camera attached to this gripper. Furthermore, in the scene, there's an object that it needs to manipulate, and it sees the object in the beginning, here, with its head cameras. And the goal is now to grasp it and put it in a destination. But the problem is, as you can see, the detected object is really not exactly where it should be. And what we want is sort of a program to compensate for this behavior. And so the robot should figure out where to navigate, where to put its base. It should figure out a way in order to get a better estimate of this position. And here it uses its sensor camera, gripper camera. Then it figures out a way to grasp this object using manipulation planning. And then once it has grasped it, it tries to put it close to itself so that it can get into a navigation mode so that it can start navigating around the world safely again. And once it has navigated to its destination, it will attempt to pick up place the object in there. And although this demo might seem very simple, it's just a simple pick and place task, there are many components associated with it. For example, there has to be a simulation environment. The robot has to know where collision obstacles are. It has to know how to avoid them. It has to know how to see the object. And it has to know if there's new obstacles in the environment that can get in its way and that it has to avoid. So this is just a short list of some of the components required to get really robust behavior for this type of simple task. And there's a recognition component for objects. There is navigation, which uses a laser-based localization. But beyond that, just if you look at the manipulation components themselves, there's really a lot of analysis that has to go on in order to make the planning efficient and the robot behave more intelligently. For example, there's an entire part on visibility and how you would perceive the object and plan for seeing it. There's a part on analyzing the robot's reachability space. there's grasping and collision safety, etc. One other thing we really want a manipulation system capable of doing is be able to quickly add a new object in and have the robot perform the same exact task except with the new object. And these particular instances of the program should be easily trainable for a non-professional without having to know any knowledge about the internal system. And furthermore, you can see here there is you can add a laser rangefinder here in order to get dynamic obstacles into the environment. So the robot did not know that these boxes here were initially in the environment, but it has to sense them and plan with them. So really the framework that we're trying to motivate in this thesis is contains 3 parts. The first is an input part, which contains all the domain knowledge and everything required for a computer to analyze and execute the task. This is divided into a robot specification and a task specification. Then we go into this construction process, which develops a planning database, which analyzes the robot's geometry and kinematics. It develops an object recognition database, and it combines these 2 databases together into sort of instantiates a set of generic algorithms with these databases in order to form the final runtime execution process. We should mention here that it's not, although in order for the robot to get proper execution, we need to have good sensor calibration. And in this thesis, we have dedicated a small section into analyzing how you would do automatic sensor calibration with this type of components as its basis. So there's going to be 6 sections that I talk about here. And I'm first going to start with the manipulation system, then talk about the planning knowledge base, the offline planning knowledge base, then go into the manipulation planning, and then ease into and then start explaining how important sensors are and how we should consider sensors in the planning process. This will lead into the automatic camera calibration algorithms, and then object recognition. And finally, I just want to say a few words about OpenRAVE, which is the enabling architecture for all these results. This is the view of a robotic system, and in some sense represents the minimal components in which they all have to interact and interplay together in order to form this autonomous behavior. All of this rests on this knowledge database components, which are generated offline. And then we have a perception component, which builds an internal world of the internal world that the robot uses to plan with. But also, it's very important, it differentiates between what are the target objects that you manipulate and interact with, and what are the obstacles that you need to avoid. Finally, we make a very big deal about the importance of goal configuration generators in the task. The task specification itself has some very high-level goals. For example, pick this object and place it here. And the goal configuration generators convert that into explicit goals that the robot can move to. And finally, the motion planning combines the goal configuration generators with the current state of the robot. There is an execution monitor that always monitors the state of the task. And there's also a visibility and feedback phase that takes the camera sensors into consideration when doing all this. So this entire manipulation field, there's so much work done in here. Probably everybody in this room has a paper that can be, has done research that can be inserted into this framework. But this is just a general roadmap. The thesis itself identifies several key technologies in each of these 5 components and tries to automate their construction process. So we'll just start with the robot specification. Besides the CAD model, you also want some type of semantic mapping of what a manipulator is, what the gripper is, and where the sensors are on the robot, and what the sensor types are. And here's another example of a robot specification that focuses on industrial tasks. Task specification itself gives you all the geometry of the world that you need, the goal destinations, and the manipulable objects. And here we assume in this thesis that there's always a CAD model of the target object that you're manipulating with. And we discuss how this is really not this is really an okay assumption, because CAD models usually exist for many objects and they can be automatically constructed. And here's another example of a task specification for industrial scenarios, where the goal is to pick parts and place them in a particular location. Okay, so because we're only concentrating on very simple manipulation tasks, we basically have a very simple task flow, execution flow, for how this entire manipulation process should go through. First, the robot searches for objects around the environment, and once it finds an object and a direct location of an object, then it tries to approach an object to better estimate its pose and its location in the world. Once this is done, the robot tries to attempt to grasp the object using various grasp planning strategies and visual feedback strategies. When grasp is successful, the robot attempts to move the object using its environment constraints to its goal. Okay, so the planning knowledge base is really, I would say, we argue in the thesis that it's really a fundamental component of that everybody should consider and should organize their information and their components in such a manner. What happens is there's user specifications that sort of are the source of all the information that come into this database. And then we start computing the inverse kinematics, the reachability, sort of very geometric heavy analyses that are commonly used in planners, but require a lot of computation to cache. And by developing this type of computational dependency graph, we can easily track how information gets processed throughout the system, and whenever something changes in the tasks, we can know exactly which component to regenerate. So I'm going to begin talking about these one by one and sort of guide everyone through where the contributions in the thesis are. So the first is the grasping, which is, in some sense, it's the most important for manipulation. And there's really, in order for you to successfully grasp something, you first need to pick a strategy. You need to parameterize the grasp space that you're searching. You need to figure out a way to evaluate the grasp. And then it's very important in this thesis, we store all this knowledge in a form of sets of grasps, which can be efficiently used in planners. One of the most popular methods of a grasping strategy, it has been used by Miller, and basically it figures out a direction to approach the object from. Once the object is close enough, the fingers close. From there, you calculate contact points, and then you calculate a force closure score. In the thesis, we discuss various ways of searching through this grasp space so that we can efficiently get grasp strategies. And we divide this into first sampling rays from the surface of an object, and then sampling rays from the surface of the gripper, and then aligning those two rays, which tells you how the gripper should approach the object. And generally, for really good anthropomorphic hands, you can fix the ray on the gripper coordinate system and just worry about sampling the surface really well here. However, for 1 degree of freedom hands, like this one here for the HLP2 humanoid, changing the direction of the ray can change the grasp from really powerful power grasps to pinch grasps. So we show its importance there. However, the problem is you get these fragile grasps very often, where geometrically they're really they have enough contact points in order to really stabilize the object. However, there's no way in the world that they will succeed in the real world. And after discussing various measures of how to detect these fragile grasps, we focus on the repeatability measure, which measures standard deviations of disturbances on the object and how they transfer to deviations on the robot manipulator at the end of the grasp frame. And we show how this method can really prune out most of the grasps of the fragile grasp and still leave a good set of stable grasps for the planning process to work with. And this just shows a couple of grasps for the HRP2 hand. And it turns out that the repeatability measure prunes out all the fragile grasps, which allows a human operator to really trust the process without having to revalidate grasping sets. And it's also applicable to this particular grasp strategy is applicable to many manipulators. We also discussed another grasp strategy, which is caging. And with caging, instead of actually constraining the object to a single point, we constrain only certain degrees of freedom of the object. For example, we want to constrain the degree of freedom of the door opening. And we show how the caging grasps can really increase the feasibility space of all this. And furthermore, we applied it in the planning process. For example, for door opening. This was done at Intel Research Pittsburgh. And the caging grasp can actually be used, multiple modalities of caging grasp can be used, not just caging, but also pushing and pulling. So as you can see here, when the robot attempts to open the refrigerator door as wide as possible, the particular handle only allows the robot to open it at a very certain degrees of freedom, 90 degrees. However, afterwards, the robot can choose a different caging grasp set and push the refrigerator all the way to getting it open. And I should mention that all these planning processes here, all the movements have been generated by a planning process where the the users just specify that they want a particular object opened.
Could you play with those other ones again? They were all playing simultaneously and I couldn't watch them all three simultaneously.
Yes. So actually, these two videos here are very similar to this video. You can see here that the robot will first use the handle to open the door partway and then try to push the rest of the way. It's in this video, the robot sees that it can actually close the door all the way without having to change strategies. Okay, so we also analyze a third type of grasp where in industrial scenarios it's very common for robots to insert stuff into parts. And this simple analysis just focused on having two magnetic tips, try to find a really flat surface. And after we build these graph sets, we can automatically begin the planning process. So another really important part of planning, manipulation planning, is inverse kinematics. The analytical equations of inverse kinematics really simplify a lot of the computations a planner has to do. And so in this thesis, we showed the theory and we developed a program called IKFast that can generate the analytical solutions of most manipulator types. And it turns out that because it's a computer, we can detect all possible divides by zero and all possible degenerate cases and handle them appropriately. And furthermore, the end solutions, most of them run in 6 microseconds, which really makes this a useful component. And here are some of the robots that analytical inverse kinematics can work on. Just to give everybody a feel on how the equations are constructed. Imagine that you have a 6-joint manipulator here, and then you have the forward kinematics here. You can start decomposing these forward kinematics equations by left and right multiplying matrices. And in the end, from these sets of equations, you can start building particular constraints. For example, the left side has to be equal to the right side. or the lengths have to be the same. Or in the case of rotations, the ratios have to be the same. Furthermore, we identified a very important usage of ray inverse kinematics. And we talk about it in the thesis. For example, if we have a sensor attached to a robot, we usually care about where that sensor points to in the form of a ray. We really don't care about its roll around its axis or that much about its z-depth. And so, sometimes we want to compute ray inverse kinematics in order to simplify a lot of the sampling processes. And this actually turns out to be tricky because a ray is a line, and we don't care about what point on the line we should hit. Which means that there's this free parameter here that really gets in the way of solving the equations. And in the thesis, we discuss a particular transformation method to get rid of this parameter and solve the IK. Just to give you a hint of what a ray inverse kinematic solution looks like, imagine the Barrett WAM arm where there's 2 joints here and 2 joints here. Then the solution for one of the joints is this, which is non-trivial to solve by hand. So we did various computations on the speed, and it turns out that most of the time it can complete from 5 to 7 microseconds. And depending on if you have extra redundant degrees of freedom, we discuss how you can handle these degrees of freedom appropriately. And you can see some solutions here of how you can explore the space efficiently of all the inverse kinematic solutions that are collision-free from the environment. Another component in this planning knowledge database is reachability, which has been studied a lot in manipulation. In this particular thesis, we saw it as a 6D end effector pose map. And we use it for many processes in the planning in order to speed up computations, which I'll discuss later on. You can see some of the reachability volumes here for the several robots. What happens is each of the colors here represent a density of the rotations that a manipulator can hit in this region. And for some robots, the reachability is really sparse, which means that you can't just place it anywhere and expect it to perform manipulation tasks. You have to plan with this reachability space. Just to show a comparison, what happens when you add a chest degree of freedom here to the robot? The reachability space really expands a lot, becomes much more dense. And so, for really constrained manipulators, it's important to have as many degrees of freedom as possible. Another component in the planning knowledge database is the concept of inverse reachability, which means that if you want the robot to place a hand somewhere in space, then where are all the possible base placements in order to place this hand there? And what happens is this is actually in the form of a distribution on the position of the robot and the angle of the robot. And we discuss ways of clustering and caching this type of analysis in order to make it really fast for the planning process to use. Because we can get a base placement distribution for particular hand locations, we can figure out what are the best possible grasp strategies for a particular object. So this shows 4 scenes here of a manipulator, of a gripper grasping an object in various rotations. And it turns out that this one here, which is coming down from the top, is the one that's mostly away from obstacles. Therefore, the robot should prefer it over others. So we also introduced a concept of grasp reachability, which we can combine grasp sets for a target object and the inverse reachability to form an aggregate map that will tell us where should the robot base place be in order to find a grasp for this object in the current environment. And we show ways of how to compute this fast and validate collision obstacles, etc. Furthermore, assume you have a scene of 4 objects here, and there is several manipulator subchains defined for the robot. For example, the left arm, the right arm, the left arm using the chest, etc. And you can combine all the inverse reachabilities together to form this type of aggregate base placement map which you can easily see once you start doing Minkowski some subtraction. You can easily see where the regions the robot should go in order to grasp these objects. And note that all this depends on the type of gripper and the type of object and the type of robot kinematics. So it really encodes a lot of this information. But also in the thesis we discuss usages and the importance of convex decompositions in planning. And we argue that convex decompositions is really important for robust planning and for being able to do 3 particular tasks in the planning process. One of them is padding. We can actually, using convex hulls, we can pad the object much better with a particular radius of safety for the object. And these types of padded models should always be used when you're avoiding objects, but for self-collision and other and approaching objects when you grasp, they should not be used. We also talk about how easy it becomes to subtract range data from that lies on already known geometry in your environment. For example, the lidar here will hit the robot arm and will hit this known object. But when you're manipulation planning, when you're planning for manipulation, you want to get rid of these obstacles here, the pink boxes, so that you can robustly pick up your target object. Finally, we discuss a more robust distance metric for configuration spaces using swept volumes. And we show that when you use this distance metric and compare it to having all weights of all degrees of freedom of the robot equivalent, using this distance metric can speed up your planning by 2 times. And also, it can make line collision checking and much faster. One of the other final components that we really push on in this thesis is this concept of the detectability extents for an object. When you want to see an object, and in order to better estimate its pose, you need to know where the camera should be in order to move it there. And we discuss a way to in fact, training these is really simple. You just have a user just wiggle the object around the camera. The object recognition program will record all the possible poses of the object that was detected. Then it will filter those and convert those into a probability distribution, which then we can sample from. So what happens is when you aim for most of the higher density regions in this detectability extents, you're guaranteed that even if the object has errors and you don't really know where it is, your camera will still be able to perceive it. Okay, so now I'll discuss how this knowledge database is used in the planning process. Okay. The planning process is really divided into 2 subsections. You have the goal space definitions, which can be explicit or implicit, that the planner must hit. And then you have something that connects a configuration space from one to another that can generate the path for the robot that still satisfies all the constraints of the particular task. And so some of the work done with Dmitry Berenson in 2007, we discussed how you would efficiently do this when the goal is to grasp an object. When the goal is to grasp an object where the robot doesn't move. And it turns out that because of IQ constraints and everything, most of the grasps are not reachable. And we have to efficiently sample in this type of space. So, but furthermore, with this type of formulation, we can consider all grasps of all objects at once, which make planning really robust. We also discuss another validation method where, as you can see, sometimes, even though this grasp is collision-free and could probably be hit by the IK of the robot, when you close the thumb here, it will collide with the object. there's also another condition here which we want to remove, where the grasp is so close to this object that there's no way that it will hit this object, that the gripper can actually move there realistically because of the errors in perception. And furthermore, you might want, when you're considering grasp planning, you might want to consider also the destination region, not just trying to grasp the object. So you can see here a video of the grasp planning applied to various robots. And all of this, all the IK, all the grasp sets were generated from the planning knowledge base. And all it required was for a user to initialize, specify the CAD models and the manipulators of the robot. The planning process itself is relatively fast, 1 to 3 seconds, depending on how heavy intensive your grasp sets are. We've also done several experiments with real robots showing that this method really does work in real scenarios. And there's a lot of magic discussed in the thesis that makes these demos work 100% of the time. Whereas if you just run a planner on it, then without considering anything else, it will fail most of the time. Another really important planning process is planning with implicit goals. For example, very often a robot will want to open its grippers to appreciate. And depending on where the arm is, sometimes the opening cannot occur at all because the fingers will collide an object. Therefore, we want to plan for an arm configuration such that the hand is free to open. And this is also very commonly used in when planning with a large degree of freedom robots. For example, this robot here wants to, we want to turn the torso of the robot to the left. However, turning it would mean that the arm would collide here with this box, and we don't want that. So using this type of planner, the robot will decide to move its hands up before it rotates. And then after it's at its goal position, you can start doing the grasp planning. Can you do the lights? Thanks. So up to now we've discussed this one-stage grasp planning process, where you have a goal space that is the object grasped, and your initial configuration, and you need to find a way to it. However, life is not that simple because there's a lot of errors. For example, perception errors can mean that you've detected your object in the wrong location. And in this example here, the cup is detected 20 millimeters away from this other cup. However, and so we plan a grasp here where the finger is inserted between the two because it's safe. However, as the robot gets closer, it can better analyze the cup and see that the distance between them is actually 5 millimeters. And the grasp becomes invalid right away. And we want to prevent situations like this from happening. So it really doesn't make sense, if you consider in this example, to start grasp planning from the beginning when you first see the object. There's also calibration errors. In this example, a humanoid here with its head cameras is observing this box, which is resting on a sink. And however, the estimated object is inside the internal world representation is 4 centimeters away from the sink base. And even though it might not always be 4 centimeters, it's error that that the planning process has to compensate for, or otherwise it cannot guarantee 100% grasp execution. So this is why we motivate the need for visibility sampling, and where there's a gripper camera or some type of camera attached to a robot that goes in and looks at the object as close as possible to get a really good, confident estimate of where it is before it starts grasp planning. And there is 3 particular components to consider when you're sampling for these types of configurations. And we show that this type of sampling is actually really efficient. It can take 10 to 100 milliseconds to sample for these robots. Occlusions are handled by shooting rays from the camera and subsampling the space. And also the detectability extents are used in order to guarantee that whenever you see the object unoccluded in the camera field of view, you're actually guaranteed that the vision algorithm can detect it. So this one-stage grasp planning process actually turns into a two-stage grasp planning process, where where this first stage here actually plans to a visibility goal space where you can really estimate your object well. And then after this phase, you plan to the goal space. And it turns out surprisingly that when you divide this, your execution process into these two steps, the planning computation time is roughly equivalent to the planning computation time of a one-stage grasp planning process. And the reason is because, the way we explain it is the visibility goals here act as a keyhole configuration, such that they divide the search space into two much more easily solvable chunks. Sometimes there can be problems with the visibility space being too big. For example, here the orange region shows where the camera could be in order to estimate this object without considering environment into account. However, there's no way that the robot can reach all these configurations, and so sampling would really take a lot of time. Therefore, we use the reachability space here to quickly multiply and prune out poses of the camera that we know are completely impossible from the system. And this leaves us with a much smaller field which we can then start sampling from efficiently. And we all these considerations sort of boil down into this type of generalized configuration sampler that considers that organizes all the particular components that you have to consider in the planning process in order to efficiently sample your goals for grasping. This is some of the configurations generated from this goal sampler. And the objects can be scattered anywhere in the environment, and the robot is able to sample its base and sample a grasp and the arm configuration simultaneously in a really efficient loop. This just shows a video of the entire two-stage process working. The base is holonomic. So in this stage, the robot now plans for a visibility configuration here, and once it's done, it will attempt to grasp it and then put it to its destination. You can see that here in a much more tighter scenario where it's not really possible for the head cameras to see the object, but it's possible for the wrist camera to get in and grasp the object and put it to its destination. When you're dealing with mobile manipulation, you probably notice in the videos that when the robot picks up the cup, if there is no other component to tell the robot to move the cup closer to itself, then the robot will just navigate like this around, which is really unsafe, and it's not what the navigation planners expect at all. The problem is that if you just have one static configuration, the robot always moves for navigation mode. For example, this configuration here. And then the robot goes and grasps the object and then moves to this configuration. It might get into collision with the grasped object. So really, the solution is to, again, plan with these implicit goals, where once the object is grasped, there's a box formed around the robot that sort of represents the navigation region that the navigation plan expects the robot to be in, and try to get all of the robot's body parts and all of its grasped objects inside this region. And this would give us a solution like this, and finally we can get the answer. Efficient. Here is another more realistic scenario of a robot attempting to grasp this object here, where it's not viewable by the head cameras. We have initialized, where the object is roughly in the system. And then the robot now uses its detectability extents to search for possible camera locations that can see the object roughly. It sees it here. And then it plans to grasp it. And note here that the boxes are really being estimated from range data coming from the laser rangefinder. And they're not in the original environment. So once the object has grasped, the robot has grasped the object, it will go into its navigation mode and attempt to put it at its goal. We also performed some experiments with bin picking, some simulation experiments. But the problem is with bin picking, and these, when parts are scattered randomly in the bin, you can't really know what all the parts are. And so you cannot really use the visibility theory just as is if you have detected one part. Instead, we argue that for bin picking, you should have these uncertainty obstacles around the target part, which actually, so this is the real scene, and this is what the scene would look like when you just have the part estimate. The robot can use these obstacles to make sure it does its visibility sampling without occlusion, and then it can grasp the object. And we have performed several experiments with various objects just to show the manipulation planning aspect of it. Here, this gripper is actually a magnetic tip, which when it touches the object, it has it. So the robot, using such simple extensions, the robot can now do manipulation planning with scattered parts in the bin. Okay, so I guess this leads me into the automated camera calibration. And what I mean by that is we have several sensors on the robot, and we need to compute where they are exactly attached on the robot. For example, here's the camera sensor attached to a link frame here. But we don't know what this relationship is between the link and the camera. But we want to compute this relationship automatically. So the way most systems do it is they have a calibration pattern which the camera sees, and then after capturing many different poses of the calibration pattern, you can actually solve for where the calibration pattern is in the world and what the relationship between the two links is. And so this would really simplify. So if we can make this process automated, in that a user would just place a calibration pattern in front of the camera and just press a button, and then the robot will automatically calibrate itself, then we will have automated the process. And so we describe ways in the thesis of how we divide the process into first an initialization stage, which computes a subset of which computes a rough initialization of the values, and then starts using the detectability extents of the calibration pattern in order to sample best views, progressively good views of this pattern, so that these results can be used in the extrinsic and intrinsic camera calibration. However, because it's a robot and we really cannot guarantee how good the capture data is, because nothing is calibrated until the stage ends, we need a phase here which computes calibration quality. And if the calibration quality of these patterns is not good enough, then the robot has to repeat the process. And so we have to know when to stop or when to continue. And before that, I want to show, here are some examples of just placing a checkerboard pattern randomly in the scene and have the robot just figure out ways to move around it safely so that it can capture its data. Furthermore, you can do the same exact process with very little modifications for calibrating environment cameras. You just attach a random checkerboard pattern onto the gripper of a robot and have the camera calibrated. For calibration, computing calibration quality, there have been many methods proposed, and we discussed a lot of them. But it turns out that when you look at previous measurement methods of how error here corresponds to the resultant values of one of the parameters, in this case it's the focal length, how these errors here really hold very little information about what, how good particular calibration is to the true value here, which is around this case. So by using some formulation, matrix formulation from Zhang and computing and looking at the patterns and looking at how the second smallest eigenvalue deviates from the null space of this matrix, we discuss a correlation between how the errors here correspond actually to how higher second order eigenvalues correspond to lower errors, so you can trust your results more. We also did some experiments with object-specific pose recognition, where the task here is you know the CAD model of the object, and you need to figure out where it is in the scene. And a lot of really robust methods have been developed for doing this with textured objects that work really well. As you can see, the object can be half occluded, but as long as you find a subset of features, then you can do these 2D, 3D correspondence matching and compute a pose. However, getting it to work with metallic parts requires much more analysis about how the features behave on the surface of the object. And so one of the first things we discuss is this object vision-centric database, which attempts to analyze how features behave on the object surface and extract meaningful, stable, and discriminable features that we can then cluster into visual and geometric words. And we've also encoded this into an SQL database to really keep track of all the particular algorithms that are in the vision database construction process. So all this requires gathering a good set of labeled data in order for us to really analyze how features behave. So we have a stage here, and the target object attached to it. And the stage goes through the object, randomly moves the object, and gathers a good distribution of how it is viewed under various angles. And because there's a checkerboard pattern here, we roughly know where the object is in the image. So what this allows us to do is, for a particular CAD model, because we have this golden labeled data, we can actually, for a particular whole feature detector, we can map where all the whole features fire on the object surface. And then, doing some statistical analysis, this is a kernel density estimator of the kernel density estimation of the density of each of the features. We can use this type of model to prune out bad features and really only leave the ones that are the most stable and fire the most statistically. And as you can see, for a whole detector, it pretty much gets all the holes exactly where we want to fire it. As you can see, sometimes there's a lot of firings here, which the statistical database, the statistical analysis removes completely. There's also a bunch of holes here that are not left out, that are not computed as stable because they're so small and they fire so little that it really doesn't make sense to use them in the pose recognition process. However, if you try to force a human to, for example, label the 3D features or extract the 3D features from a CAD model, then most likely the human will say that these are 4 points that the whole detector should always match and go from there. And such assumptions are really do not have a good statistical basis, so they won't work all the time. We can also do the same thing for lines, where we figure out where all the expected lines are with directions. And this allows us to filter out bad features and leave out only the good clusters, which we can then generate the set of geometric words of what type of line clusters we expect an object to give us, which allows us to compute pose estimates from the image using this new method called Induced-Set pose extraction. And the idea here is that if the camera observes a particular feature, that it knows exactly what poses it came from, and what poses are not possible at all. For example, in this case, the corner cannot be viewed at all because the rest of the object blocks it. So, furthermore, we can do this for lines, SIP features, any type of features possible. There's no limitation. And I'm not going to have enough time to go through the details here, but basically, the pose extraction process, because if you single out a particular feature, you have a bunch of hypotheses that go through this feature. And for another here, and what the pose extraction process does is it randomly selects features, 3 or 4, takes their intersection, and it sees if there is something in the intersection that is meaningful and not random. And so we can do the same thing for lines. This actually turns out to work pretty well for these particular parts here shown. We've done tests on.
Before you go on, just really quick.
Yes.
What's the coloration in the imagery?
Give me 1 second.
Oh, I'm sorry.
Okay, so the color is a particular image capturing process. It is just meant to give contrast for the edges. It is not part of the algorithm.
Artificially induced, or?
Yeah. So the way we do this is we have 3 lights structured on the surface, and each of the RGB channels is one light channel. From there. Okay. So in the end, I'd like to conclude with a small discussion about OpenRAVE. All the technologies in this thesis were really possible with this architecture. And this architecture was developed as a consequence of all the manipulation done for this robot. The OpenRAVE is divided into, I would say, 4 components. There is the core component here that defines a really solid API that users can use to convert their libraries or use their modules into OpenRAVE modules, which can then be used by other modules. This core contains an environment which sort of holds your state, and you can clone these environments and do multi-parallel, multi-thread processing, and a lot of neat things with it. Most of the functions in OpenRAVE come in the flavor of plugins, which are just dynamically loadable objects, and most of the theories and algorithms discussed here are already come in plugins. Then there's a scripting environment which makes debugging really, really simple. And finally, the robot database, which I discussed, which handles all the automatic generation of the planning database. And I would say that this here has been a great success. There is about over 100 users now, and there's a really active mailing list, and the number of tutorials for OpenRAVE are increasing. There's a lot of, and it has been used with many, many robots, which sort of has filtered all the algorithms that don't work and just left the ones that do work. And in the end, the message I want to send with OpenRAVE is that everyone benefits with open source research. And in some sense, having OpenRAVE and having constant feedback about OpenRAVE sort of transferred into feedback about your research and where things still need to have more work, where people have trouble using. And this has really allowed us to sort of develop the ideas behind this manipulation framework through an open environment. Finally, I want to close with a statement that manipulation is hard, no matter what anybody tells you. It is very, very difficult. And you can do all your planning and simulation as you want. It will not run on the robot unless you really sit down and think about the problem. Sort of in this thesis, we've tried to identify several components that are used a lot in the planning processes, and in the past have been mostly generated by people, but can now be automatically generated. And we definitely have not solved all the problems in manipulation. There's a lot of problems left, but hopefully this should serve as a way for serve as a framework for people to consider sort of a robot task compiler when training a manipulation program. Instead of just, and this compiler will eventually, hopefully one day, replace a lot of the manual processes that are done today to get manipulation programs running. This structure, so I just want to say that in some sense,
could you connect the Skype, please?
in some sense, automating the most simple tasks, like pick and place tasks, is the next step in automation technology. And hopefully we can see more of that today. I would like to acknowledge these four institutions: Quality of Life Technology Center, Intel Research Pittsburgh, University of Tokyo, JSK Lab, and Lua Garage, for helping with a lot of robot experiments. Yes, you, Mike, by the way. Everybody has been a great help, and without them, none of this would have happened. Thank you.
Okay, so it's our tradition, Professor Okada, that outside members start question session.
So, Rosen, what is the conclusion of your thought?
The conclusion is that by considering the compilation process as an explicit component of a manipulation framework, we can start organizing the information inputted into the program. What information can get automatically analyzed from this, and in the end up with a set of static analyses that are really useful and really help manipulation programs run.
So, if we take a robot compiler, what's the key point of making such a system or program or architecture or method? What's the key in the robot compiler?
Yeah. So the question is, what is the key of a robot compiler? Why would you need this? Think robotics being a very heavy information sort of. There's a lot of information processing in robotics. There's a lot of components that people have to tie in together to get things working. One of my goals was sort of to start at least start with a small structure that encodes these types of relationships much more explicitly, and in the end only gives the user the specific these specifications, and these specifications tell the user that he doesn't have to worry about anything else in the system except that knowledge. And we've attempted to, using these specifications outlined in the thesis, we've attempted to generate all the models and all the processes required from them in order to get a,
Yeah, so suppose if we have a nice compiler using, for example, 10 or 5 years ago, what
so much to do. In fact, as you can see, one of the assumptions in the thesis that we stated is we just care about reliable manipulation. And we've outlined sort of the minimal set of components that will make this possible. And there's a lot of research to be done with when people get into the environment, being safe around people, doing more sort of dynamic tasks where there's really explicit constraints that you have to solve all the time. And we don't discuss any of them. We just discuss sort of the general, most simplest scenario, and we try to make that as automated as possible. Because in some sense, if you look at factories and robots today, there is really not many robots using motion planners in factories. Because a lot of the fundamental problems, before any of the cool, interesting questions are answered, are still not automated. So I think there's a lot of research left in manipulation.
So you have done from vision to manipulation. I mean, you have done a lot of work during your PhD course. What is the most difficult part or critical part?
I guess the most difficult part would be the interplay of all the components. You can get one component really well functioning and within your problem specifications, but once you start connecting it with others, this breaks and things stop working. And it takes a lot of time to find out where the problem is and where the bugs are. I would say that getting all the components together into a functioning system is the most difficult part, and there's still a lot of research to be done to make that much more automatic. We've only covered, I guess, in terms of component relationships, we've only really covered how the knowledge database relates to each other. The knowledge database components relate to each other.
Yes. I'd like to pass to other professors.
Okay. Paul, do you want?
Are we going to have a second phase of questions after this? I mean, so how are we doing this? Do I ask all my questions now, or should
You can choose anyway. I think go with half of it.
Half of them?
Yeah.
Okay. We'll do the half ones. I wanted to get your thoughts, maybe sort of as a follow-on to the previous question about the utility of the robot compiler and how this would work. Is from a high-level perspective, you mentioned earlier that your hope is for non-professionals to be able to take a robot and basically program it very easily. In your estimation, have you simplified the problem in terms of time, effort involved? And this may be a leading question, and I apologize, I'm not sure how to formulate it better. Or have you moved that complexity somewhere else? Because the compiler does a lot of automated things, which simplifies things you don't have to do anymore. But it does seem to require what seems to me in the onset a large amount of additional information in the databases and the CAD models and all these other components. So it's hard to quantify.
Yeah, I think I see where you're going.
But can you speak to that at least?
Yeah.
Can you understand what I'm saying?
Yeah, that is very interesting. So from my experiences with dealing with some of our industrial partners, they're very smart people, but they are really not manipulation experts or planning experts or vision experts. So they can gather data, training data, they can execute simple programs. And but when it starts coming to tweaking planning parameters in order to get fast execution or doing all these things, like base placements and etc., they're really not going to be much help. They need more knowledge in order for that to happen. And I guess that's one of the reasons why you see this division between the user input, which are basically people with sufficient knowledge in robotics and industry can specify, like CAD models, training data for images, and then sort of the analyses, which are like the inverse kinematics generators, the reachability stuff, the detectability extents, and how you use that, and all the parameters for that. We've attempted to make them as automatically generated as possible, or at least have provided intuition of how you would do that, so that eventually you end up with just having to run the planner. And perhaps, although this probably needs to be quantified better, perhaps have very high level parameters of what can be tweaked into a system.
I just had some comments about the presentation itself. When you're talking about the grasp, the grasp plan and the validation of the grasps, you mentioned that all the fragile grasps are removed.
Yes.
Does that come with the price of potentially throwing away good grasps?
Yes.
What happens with the threshold?
Yes.
So what's your feeling for where you set that threshold?
That's a really good question. In fact, that's one of the reasons why in the end we chose a repeatability measure. There was other measures, for example, other attempts to reject grasps, earlier attempts that attempt to complete force closure and attempt to evaluate the measure after disturbances have been computed. And this rejects a lot of the grasps for anthropomorphic hands like the bird hand. For example, 80% of the grasps would be rejected. And for a 1 degree of freedom hand, using these types of earlier measures, 100% of the grasps would be rejected. Whereas with repeatability, because you can adjust the threshold, in some sense, the repeatability measure somehow captures the essence of what a fragile grasp is, which means that the grasps cannot achieve that particular orientation, a particular position with respect to the object. It slips or it does something, or it can easily slip. And by computing these standard deviations, we have shown that we can actually reject all the fragile grasps while still maintaining about 50% of the stable grasps. And we discuss various trade-offs in the thesis.
Could you go to the slides about IK-fast? Slide 25 and beyond. I have a couple questions there, actually, for clarification. Okay. You talked a lot, or I shouldn't say, you introduced this very quickly. Can you talk about what the specific theoretical contributions of the IK-fast algorithm are?
Okay, that's a good point. When you try to compare it with other methods, so other methods have solved the inverse kinematics analytical equations, except they're very math intensive. So the computations required for you to get a solution involve a lot of operations. And there's singularities. For example, it requires a 48 by 48 inverse matrix and the eigenvalues of them in order to compute these analytical solutions. The difference with this method is we take the algorithmic approach, where we search in the space of all possible ways you can set up the equations. And within the space, you can find out the shortest, the most stably computable, the one that has the least divisions. And sort of prioritize which joint solutions get solved first, depending on the stability. And so I would say it's more of an algorithmic contribution rather than a theoretical contribution.
About that, I mean, are there approximations going on because it's a sampling thing? So you might miss like optimal solutions, or am I misunderstanding?
So you're always going to get an accurate solution. The thing is, there's multiple ways to compute a joint value, and each of them require X number of operations, and usually it all depends on how your floating point arithmetic works, even if you're using floating point arithmetic. I would say that by you not choosing the most optimal and fastest solution, in the end you're suffering about computation time, and you might have a little bit imprecision later on. However, if we're dealing with 64-bit numbers, this imprecision is so small that most of the scenarios here don't really... most imprecision comes from the arctangent function in a computer, right? It's about imprecision like that can get in the way. So we've discussed various measures of how you would prioritize which equation to use over another, and there's actually a hierarchy of prioritizations depending on how the structure works.
You should probably point out when you explain this, the example of a hand-coded solution to the IK that misses so many degeneracies compared to the automated version.
Yeah.
So I think that's pretty impressive.
In fact, I've compared one of my previous hand-coded solutions with generated solutions. And the generated solutions are much longer because they cover all the degenerate cases. But they're just as fast because in the end you're just jumping through code in order to get the correct scenario case. A human eventually gets tired of handling all these cases and just says, at least returns failure if such a case is detected, which is actually quite often. So.
On slide 31, we talk about the results. There was a couple instances where the IK-fast failed.
Yeah.
Can you speak to maybe whatever small percentage of this, why they failed and what?
So this is a really good point. What happens is, when you have 7-degree of freedom arms or more, you have to choose a subset of those, 6 of them, to do the IK. Because the IK for 6 dimensions only works with 6 joints. And you have one free parameter, which the user sets ahead of time, and then queries for a solution. And the way this happens is we actually search using a particular discretization factor of this free parameter. And what this is showing here is, so most of the time, for most arms, we chose the free parameter to be the one that is furthest away from the base joint, because the base joint sort of affects the robot the most. So we want the furthest away such that the whole chain is still solvable. For the Willow Garage PR2, we chose specifically the base joint. And when you choose the base joint, and when you have the same discretization factor, you see that success rate drops because sometimes the solution is in between the discretization factor. And we showed this by making the discretization factor 5 times lower, and you see that the success rate goes up. So all these success rates are failures of solution. There's never a case where a wrong solution is returned.
Okay. Can you go to slide 58? Okay, the visibility sampling is really interesting. There's a couple of details I'm a little unclear on.
Yeah.
What's the initial knowledge of the robot when it first starts? I assume that a camera can see the object,
Yes.
can recognize a rough pose of the object, so at least you
Yes.
get some idea of the heading or the pose, so that you can get closer and then hopefully get there. So that's kind of the assumption there, isn't it?
Yeah. Actually, one of the first scenarios I covered here is exactly where the head cameras see the object, but it's not reachable yet.
Right.
And here, in fact, you see that the object is halfway inside the scene. So the estimate is pretty rough, but you can still use it for visibility sampling.
Right, and so the question I had was like the examples you had with like the Fruit Loops boxes. It looked like, at least from the 2D pictures of it, of the 3D visibility sampling, that this was my Fruit Loop box, right, or my phone. You know, all of the points of visibility are out here because that's where you can see the face.
Yeah.
So at that distance, it still knows whether it's kind of like this or like this somehow.
Yeah. There's. Yes.
Can you quantify exactly kind of what the rough order of magnitude of the error is?
That's a good point. So in the thesis, I discussed ways to quantify this error by using a robot arm to capture the process, to capture the detectability extents. Because when you use a robot arm, you know the relative positions of the cameras, right? And so you compare that with the relative positions of the vision algorithm, and you can get a rough idea of how much offset you get from that. And then obviously you would prune configurations, you would prune pose estimates that have a very big offset. Without a robot arm, this is very difficult to quantify. In the end, we stuck with the assumption that sampling in the most densest regions first are the most stable, will give you the best solutions. And then we just sample around.
Yeah, that's okay. Just have a couple more here and I'll pass the token. In the automatic calibration section, have you done any analysis to know whether the problem is in fact sort of converged to a global optimal, or if there's sort of a local optima that you could accidentally hit and then be stuck in?
Yeah, that is exactly the problem with getting at this, automating this phase. Because, let me just turn into the image here. What happens is, let's say you have 10 images that you've gathered. And some of these images, and you've skipped maybe 15, of the 15 that you want to gather, you gather only 10. And these images don't constrain the parameters really well, the calibration parameters. So in the end, calibration is an optimization of the reprojected error of the pattern. And you can have that reprojected error 0. In fact, the less number of images, the better your reprojection error is. But that doesn't mean that you're at the optimal at all. In fact, this is what this graph is showing here. Right. So in order for us to really trust our results, we wanted to somehow figure out a good measure that gave us some indication of whether we were at the optimal or not. And this is where the second eigenvalue measure came in, that I guess after testing various parameters. And we discussed why the second eigenvalue makes sense. But in the end, the higher the second eigenvalue is, the better, we argue that the more confident your solutions are because they can be solvable on. And we show a progression graph here.
Now, is that provably optimal, or is
provably
we're not sure yet?
Provably optimal.
Sort of the best
we're not
heuristic
sure
algorithm.
yet. I think right now the thesis just gave results analyzing that measure and gave an intuition of why this works. I'm not it's actually very difficult to say provably optimal because in the end there's sensor noise.
Absolutely.
Right, for reprojection error. And which is why a lot of the previous measures, like the ratio of eigenvalues or singularity, however you would test, they didn't perform so well because the noise gets in the way of sort of getting your really theoretical good results about it.
Last question. When you did the Vision compiler, and especially on slide 76, or sorry, 78 was actually pretty good for this. You have a sense for, is this good for a certain class of objects which have very unique structure, very defined holes or features? I'm just thinking about my house, and one day the PR3 may be going through my house someday, and a lot of my possessions don't look like these objects.
Yeah.
Particularly since I have kids, I have lots of stuffed animals and stuff like that. Can you speak to the kinds of objects that would be poor for this, or where you think it might not work?
So the way we've formulated this is you have a feature detector. It can be a point feature detector or a line feature detector. And this detector has, along with the geometric position of where the point is, it has a feature descriptor. And what we attempt to do is we try to see which descriptors are most stable, they occur the most, and they're localized the most with this shows. So in that sense, I would say that any object would work and you would get good results. The thresholds that we have,
assuming you had the right feature detector.
So that is the question, right? What is the correct feature detector to use for a particular object? And I think this type of analysis would help that, because you can see what type of stable features are for a feature detector. And if one feature detector, for example, was all blue here, right? Like features are just random everywhere. Then you would have very little stable points. So you would say that this feature detector really doesn't give us much information about the object, so we shouldn't use it. And we have attempted to reverse, to use this process as a design process for a feature descriptor. Because a feature itself has many parameters. And you can tweak those parameters to get just the settings you want.
Yeah. I mean, this works well for these industrial parts because you've got lines and holes and edges, I mean, you can break any feature detector by just having a big shiny mirror ball or something really specular, and they'll just break it.
Yes, but I argue in that case...
No, I mean, I'm saying it's a...
This would capture that. This would actually detect this case.
If you have like a specular mirror ball?
Yes, if you have a specular mirror ball.
Features.
Or if you have reflections. For example, if you have reflections on your object...
But then they're environment dependent.
So it is, which means that you need a big database. Right. That's what environment dependent means.
Well, then...
So, but then the feature descriptor itself, why do people do vision research, right? To get good feature descriptors that are environment independent or pose independent or something independent to simplify the process. And this is one stage, I would say, that people can use to automatically gather data and sort of reinforce their results of what they think about the feature detector.
I'm done. Good. Jay?
Okay, so as a planning person, it's always been the tradition that they ignore a lot of dynamics, and it's very geometric and kinematic. And that's definitely true also of this thesis. Like, I didn't hear much about force control or torque, things that if you look at a lot of manipulation research that people believe is really important, tactile feedback. So in your mind, what is important, or what can be enabled if you have these kind of things, or how do you actually turn this into something where you're talking about manipulation dynamics or grasp dynamics?
Okay, so I think there's two questions here. One is why choose a subset of why you choose to ignore torques, and the second is how you would incorporate torques and dynamics. So to answer your first question, if you look at most robots today in factories, they're really static. They're doing repetitive tasks all the time. There's very little sensors on them because it costs money to put sensors on. So I want to sort of focus on those constraints and develop better automation technologies for that specific scenario, where you don't have humans involved. You don't need to be safe. You just need to reliably execute your task. So how you would integrate dynamics into this framework? I would say that's a really big question. In the end, if you look at where dynamics is used, it's mostly in the execution process, right? Where you need reactive behavior or something. And yes, there's inverse dynamics equations that people use to get torques, to relate torques and joints and stuff like that. And I would say that those maybe can be cached in some type of the planning database, or these types of specification databases. But mostly it's execution oriented. And I would sort of restructure in fact, a lot of the architectures analyzed in the thesis, like the Alice architecture, sort of integrate dynamics and this type of learning cognitive-based motion behavior in the deepest core level of the system. And then they sort of build up their hierarchy that way. I would argue that although such architectures are very useful and very, from a scientific point of view, probably should be studied much more, they're not necessary in factory scenarios most of the time.
So, fair enough. I think you have a decent answer. I was actually expecting you to say something about the tasks that you're looking at. Like, for me, pick and place tasks. If you're not trying to do two-handed assembly, right, or something that requires sort of managing internal forces, that you can get away with sort of a lot of these kinematic and geometric approximation tools and things. I think if you are doing sort of insertion of a peg in a hole, or something that requires sort of force feedback that is quite vital to the success, then it might be more important.
Yes.
So, I think it's totally reasonable to actually build research infrastructure for tasks that don't require a lot of dynamics, like pick and place operations or bin picking or something like that. So I think you've actually you have tasks that fit well with the work that's been done. But I think there is probably this whole other space of tasks.
In fact, just to add on to that, a lot of people use dynamic simulators to sort of get this predictive behavior inside their planners. Right? But I would say that today, especially when friction gets involved and all these uncertainties, we really don't have a good dynamic simulator for robotics. Which is one of the things that are preventing us from moving into this step. But if there is ever a next step for this type of manipulation framework, it would be to add that slowly.
Okay. So can you go to the section where you talked about the convex decomposition? I know you have a much more in-depth coverage of that in the document itself, and you skipped over it a bit in your talk. But I was actually intrigued that you said that I didn't quite understand when how you were saying that can you go back to the joints? Yeah. So you said that it's useful for collision detection. How much of a difference does it make if you just take a CAD model and then do motion planning versus using the convex hull? I know, probably you get an order of magnitude reduction in triangles.
Well, so the algorithm used for triangle collision detection is the separating axis theorem. That's the exact same one used for convex hulls. So basically, the number of pairwise triangles you have to compare and the number of pairwise convex hulls you have to compare are directly, that computation time is directly proportional. So when you look at these triangle meshes here, there's about 30,000 triangles. Whereas in the convex decomposition, there's 200.
Yeah.
So, and that's not it. In terms of the time complexities, that would be it. But in terms of getting more, what happens a lot with triangle meshes is you would have these degenerate triangles which are very long, and collision detection breaks a lot with them. Whereas with convex hulls, especially with padded convex hulls, you don't have these edge cases. Like most of them are pretty well rounded, and because they're very well rounded, they're more computationally and numerically stable. That's the points I argue for this. I included in the thesis just to make it more complete and to say that everybody should be using this. Right now, a lot of people still use triangle mesh collisions, and I think this should change. I don't offer an algorithm on how to do convex decomposition. I say that right. Using an already known algorithm is how you would apply it to the manipulation problem.
But you said you should use the meshes for self-collisions?
No. Self-collision, no. I mean, as you can see, this is already self-colliding. Yeah. So this actually, this type of analysis actually sort of will, it indicates that you would need a separate mesh for environment collisions and for self-collisions. Whereas right now, a lot of researchers use both. You use one single mesh for doing both self-collisions and both environment collisions. And I argue that this is wrong. Because in the end, you're always going to have a padded mesh, but the more you pad it, the more self-collision you get, and it just doesn't work out. That's great.
Okay. I'll maybe pass the baton to
I actually have one question about the relationship between your framework and OpenRAVE. OpenRAVE is the manifestation of the framework, or is that a toolkit to do your framework, to execute your framework?
Well, I would say those are the same thing. Because in the end, the framework is just presenting a bunch of tools that can be used to automate the process. And OpenRAVE has each of those tools programmed already and gives the users a very nice interface.
So considering all the tools and components that you described are in OpenRAVE, this thesis could have written as OpenRAVE as the center of focus, saying, here is the system, which you call OpenRAVE, which has all the components that you need to do automated, if not all, but let's say for now, many automated construction of robotic localization programs.
Yeah, you're right. You could have discussed it in the having OpenRAVE as a center point. I would like a more theoretical approach first, and then say here's the implementation of this. And in fact, in the OpenRAVE chapter, there's a lot of real-world issues discussed on how you would organize this architecture so that people don't get basically it makes it easier to implement the manipulation stuff. And that type of software engineering analysis, I would say, is not robotics, is not that much robotics oriented, which is why I wanted to split the two.
I think to me, that is one of the things that is a little making this understanding the value, the enormous work that you have done, the sense of sort of cohesiveness
because I think you separate the two, you may want to think about that a little bit. It may be too late. I should have thought about that much earlier. As I had that lingering feeling for a long time, and then today when I hear this as a whole, now I realized where does that little bit fuzzy feeling came from?
I see. That is very tough. Because I guess implementation details are not that interesting to most people, right? So how are you thinking of integrating OpenRAVE into a more?
I think you present the OpenRAVE, here is the idea, and then of course you can say all the things, and then at the last chapter, of course, you can say this all the consideration that it went to.
I see.
In real world consideration, which is of course very important. But by the way, we're engineers, nothing wrong, and I'm very proud of taking care of all the details and the ad hoc or anything that needs to be taken care of. I think thinking those are not important or not a part of engineering or accomplishment, I think I don't feel that. The reason that most theses don't ever use is that most of them don't take care of them. That's why.
It's the robotics people are particularly forgiving of this. I think there's a lot of, it's the traditional academic tension between what is science and what is engineering.
Mm-hmm.
Some say, I'm a scientist. Engineers, they just deal with those details. But robotics people are like, we have to be both, so we're totally fine with the details. We know that's what makes it work.
Okay.
But maybe Takeo, do you think it would be better if the implementation or the instance of the implementation, which he describes a method or an algorithm, but then he's also got an implementation that works. If that's more tightly integrated in your mind,
it could. I think maybe at this point it may not be as productive. But I was wondering, in order to make your points, right now it gives some feeling as if the first part and the last OpenRAVE chart is almost independent.
Okay.
That's not good.
Yeah. Well, you could maybe point to, so you're talking about the document as well.
Yeah.
So you could maybe have pointers to each of the chapter 8 sections in OpenRAVE where you say this has been fully implemented and tested as this plugin in OpenRAVE, which serves as a proof of concept implementation that's open source and available.
Well, implementations change, right? So the thing is, after 5 years, something's going to change, and the thesis means that it will be old.
I'm not, by the way,
so
advocating that you will change all the sections that you have, for example, inverse kinematic and so forth. That stay as is. But the point is that initially I still have this feeling that what you call framework is a little fuzzy. Whereas if you say, here is the system, or architecture or toolkits or whatever you call it, OpenRAVE, that manifests this overall framework or overall approach to how to constrain it. And for that, I have developed this theory and so forth and so forth. That's easier. Whereas you say somehow this fuzzy word framework, and then I still wondering what is it, and then they say here's lots of things, and finally there's a new chapter says, by the way, I have this thing called OpenRAVE that's usable by many people.
If I could comment here on this actually, when you did your topic defense, I felt that it was very implementation centric, and I think we talked about that. Saying I did OpenRAVE, and then we built those components, and said, well, what are the contributions? What's new in robotics out of this? And so you did I thought you did a fabulous job in following that direction. all your contributions are laid out, why the IK fast, the Vision compiler, all these things are very well laid out. And then you say, and it's bound together by this OpenRAVE framework. And hearing you guys talk, I think there's sort of two potential solutions, or maybe the difference like one and a half, in that the introduction of the thesis, the document, I think needs a little bit more oomph. And I've written some comments about it. Nothing more nothing new you need to add. Just like copy and paste a few things to make the introduction stand out as this is the intro. You don't have to wait till the end to get to the exciting. But this isn't supposed to be a mystery novel. You're supposed to know what to expect at the beginning to be really excited about it. So I would argue that you could probably add a little bit more to the intro and say, well, here's the problem definition, right? Because that's what theses are. They're defining a new problem. And then here's the framework in general, and then I've also implemented a solution to this with OpenRAVE. And so maybe you just copy and paste a few OpenRAVE pictures and write a little bit of connecting things to say, here's sort of the solution. So it's sort of connecting the problem definition, the problem statement, the framework of the solution, the theoretical framework of the solution, and then your implementation. And then as Takeo says, and James mentioned also, is that for each of these implementations in the different chapters, you might say as well, and OpenRAVE was used to control this robot to do this, and then OpenRAVE was used to control this robot to do this. And then the half solution might be, maybe the OpenRAVE section should actually be an appendix rather than a chapter, because that goes into, this is like the OpenRAVE documentation. As of the writing of the thesis, this is where the structure stood. Sort of carve that in stone and saying, here's the snapshot in time when OpenRAVE existed, this is how the thesis was done with it. And then at least you'll see how OpenRAVE, which is a very significant contribution in and of itself, was used throughout the entire thesis document, every experimental results, and the reader sees that more as a compelling narrative that goes through the document as opposed to being surprised with it at the end. And I don't think that would require a whole lot of extra work. I mean, the intro needs more oomph, like I say.
I think so too. Right.
But I think just you don't have to write a lot of new text. Just kind of copy and paste some things.
I mean, so you provide a very good point, and somehow, now that you guys mentioned all these problems,
No, they're not problems.
Consistency problems.
A little bit, nothing.
I would say that it might make more sense, perhaps, to not even concentrate on implementation details, right? Because what are implementation details in the context of architectures? Here's an operating system. Here's how you manage your classes, etc. Right? Here's how objects get loaded, and this is possible user cases. So you start adding the user into the loop when you start talking about the work, right? The architecture. And you're like, this is how the user might interact, and yes, user needs to debug stuff, so you need to do this, this, and this. And perhaps adding such a user-centric point of view, having such a chapter that does that, might not fit well with the thesis at all.
Well, so that's what I was saying, that maybe the chapter 8 could be
so
appendix A.
But even more extreme, just completely remove it.
No.
I think you're doing yourself a disservice by doing that. I don't see user this, user that. I see this as these are some of the implementation details that were in effect when this thesis happened, and that's perfectly fine as some appendix. I mean, I've seen theses with source code, as appendices, right? So there's nothing wrong with that.
Okay.
I think you should not take it out.
An idea. By that, now you can actually take advantage of the fact that you can even add more of lots of details and a lot of special things and so forth, because now it's a part of appendix. So you actually have more freedom to make it as independently claiming even potentially somewhat different aspect from the main thesis. Whereas if you put it in the main part, it has to be consistent.
Right.
Because of that, I think it's halfway consistent.
Yeah.
But by removing it, you can say, oh, I don't need to be consistent in that sense, but you can put as much as information that other people may want. And even the kind of thing that you're saying can be included too.
Yeah.
Because
that's a very good point. Just basically have a second story as an appendix.
Yeah.
Exactly.
Which sort of changes the viewpoint a little bit.
That's right. Yeah. Okay. And the other, I think, interesting thing throughout the theme. Well, I think one thing I like to have a comment from you is that it seems that approach-wise, you're mostly random, if not always. The sampling idea is sort of the undergoing computational theme of lots of things to make to work. Did you discuss that in the thesis?
I discussed that a little in the actual. The way I mentioned it here in the actual content is. Oops. Give me 1 second. Okay. So you have explicit goals and implicit goals.
Mm.
And explicit goals, the way you can actually put them into a planner is by sampling. That is, I guess, where the general approach that I take.
And then even the, even the vision compiler things is a lot using lots of sampling concept as well, I think.
Some, yeah.
And I think it's interesting to have your thought on it. And that.
Yeah, that's a very good point. I mean, I guess parameterization versus sampling.
Exactly.
And there's a lot of good works with parameterized models, and they're very quick, but they can be a little brutal at times. Whereas having grasp sets, having samplers, etc., allow you to represent the space much more flexibly.
Yeah, exactly. I think it seems that you have that theme, and many, I think, to me, that definitely contributed to success of many things here, which obviously, if you do it too parametrically, then it becomes too individualized process. While you're doing more or less sampling, that taking advantage of the computational power, many seemingly different kinds of problems, you are using exactly the same approach, same type of things. I think that is a good message.
Well, I think this type of idea has been, in the planning field, this is a very, I guess, big idea that just use samplers instead of, and I think that's one of the reasons why rapidly exploring random trees works so well. So I'm not sure how much, maybe have like a subsection or paragraph on it saying parameterization versus sampling.
Rosen, how about this? I think, in my opinion, a lot of these sampling methods were not practical 10 or 50 years ago simply because memory was limited, and storing thousands of grasps or storing the reachability set of a practical real-world manipulator couldn't fit in the memory of a machine, whereas now it's easy.
Mm-hmm.
So I think one of the things that you could write as explaining sort of the undercurrent of the sampling would be we're actually taking advantage of the fact now that memory is cheap and disk space is cheap, and I can in advance sample a lot of these hard problems and model them statistically through a database that used to be too big to store on a machine, but now fits easily on a laptop or even my cell phone. So I mean that could be one way that you could sort of see the shift toward sampling, which enables a lot of these things to happen nicely, is enabled by the fact that memory size and expense has gone
so I completely agree with you. And this type of, but I don't think this is a novel idea. Right? It's just something to fill in the reader.
Well, yeah, I mean, just to explain the undercurrent of the ways that you've leveraged sampling. You've leveraged the growth of memory and the cheapness and availability of memory and disk space in order to make things work. So it's something that you couldn't have done 10 years ago.
Yeah, even this, I think sampling, by the way, includes both sampling within the computer for remembering and planning purpose, as well as sampling in the real world, which you're doing actually for automated calibration case.
Yeah, and also figuring out where to.
Exactly. You're in a sense sampling in the real world setting, rather than trying to solve it and say, what is the best procedure to do, say, calibration and compute the best equation? Yeah, I think the theme is there, so it's very interesting.
Okay, interesting. So perhaps put that in the introduction and say how we solve this,
Yeah,
how
I
we
think
approach
that will
solving
definitely
this
make
problem.
this whole thing more further in sort of a single theme thesis, which always good thing. Okay, I think Professor Kara, you have more questions. I think Paul, you have a second series of questions.
Yeah. I have one question. I mean, so I really like the compiler idea. And have you ever thought like its relation to analogy to computer software? I mean, so it's like I feel like what we are doing is just making a Fortran compiler in definitive.
Yes, yes. So this has been discussed among us many times, yeah, I think that you can make the analogy, but the first thing you have to do before you can start talking about a robot and task compiler is clearly define the extent of the problem and the space, because like assembly language compilers and computer compilers, the operations that you can do and the problem that you're working in are clearly defined. There's memory, there's a CPU making these instructions, and maybe what we could do, perhaps maybe as future work together, is sort of taxonomize exactly what is required for manipulation planning. And this is all the components, and now we need to compile them together to form the final behavior. And that's a very good. I'm glad you like it.
I thought like, for example, GCC used to be a GCC compiler, but now it's a, it's general compiler.
It's a general compiler?
Yeah, it's a,
oh, interesting.
GCC is a G computer software, G GNU compiler collection, right?
Interesting.
So what we are doing is now we are making the compiler for tier 2 and tier 2, but in the future we can make a general task compiler for any kind of robot.
Yeah. Yeah. I like that, yes. Task compiler, exactly. You encode the robot, all the robot parts specifically in every single task, so that online you have to do as little computation as possible. Yeah. Let's do that.
You have a new task.
Let's get the ball rolling.
Paul?
Okay, so that follows right into one of my bigger theoretical questions I was having. I was reading your thesis. Probably while I'm having lunch here. As I was reading your thesis, talking about this two-stage planning where, yeah, you don't want to start your grasp planning when fundamentally your thing you're trying to grasp is far away, you have a lot of sensor uncertainty. Which makes perfect sense. It casts my mind back to when I was first learning AI, back to an undergraduate, to symbolic planners, task decomposition, the general problem solving for the GPS, and all of these sort of fundamental frameworks where you'd say, you go to the store, first you do this, then you do this, then you do this, and there's a solve as strict-based plan. And you're talking about compilers to do all these things, these steps, much more complex things, operations, and yet at a high level, somehow it comes back, it seems very similar to this notion of now we can actually solve these incredibly complex strips-based plans that people were talking about way back when, like go to the store, well, how do you do that? And suddenly we have a framework that can do it, and computers that can support it, and sensors that can do it.
Yeah.
And I'm wondering if you can just comment on this, is this an appropriate analogy? Is this probably the right way that we can do task decomposition at a symbolic level? Or is this still in the framework of manipulation only? And where does the boundary lie?
Okay, interesting. Where does the boundary lie? So, I think one of the biggest differences between, I guess, the decomposition is done here and the ones you would see in symbolic programming is that here it's already grounded into the world. It's geometric. You can't get any more specific than this. Where symbolic decompositions, you have semantics involved, you have a lot of high-level components, and they describe a concept rather than a particular scene analysis and geometric, do all the geometric stuff.
Right.
So I think this framework would actually serve as a basis for grounding all the symbolic planners.
Which was always the problem.
Which has always been the problem, exactly.
It's always been the problem.
You want to grasp an object, or your symbolic planner says grasp X. Now and then, this will tell you exactly where to move and how to do it, do all these analyses. And in fact, I see the task level planning and decomposition as the next level for more complex behavior. And there's a lot of work done in this area. Like I on purpose didn't put, I just mentioned it in one little paragraph and on purpose try to ignore it most of the time anywhere else in the thesis because I don't want people getting confused with task level planning and the geometric based stuff. However, sometimes there is this first and second stage stuff, which I think are very useful observations and maybe discoveries that a lot of people should in the future encode their task level planners to have these types of stages. But I didn't try to venture out any further than that. I don't know if that answered the question.
Kind of gives me a feeling for it. The second question that I had, so that was for the strict level planning, and kind of going through the history of AI now. The second thing that has struck me, this is a perfect slide to stick on me. This is where most of my background comes from. Now, I cut my teeth on behavior-based robotics. I first learned Rodney Brooks's philosophy back when I was an undergraduate, so applied it as far as I could go with it for a long time. And my first thought when I saw this, just at a high-level concept, was like, yeah, well, no kidding. First, you have a behavior that drives up to the thing. Then you have a behavior that grasps it. You don't have the behavior that does all the things at once. First up. So theoretically, this seemed very, very, very intuitively obvious to me from already breaking the problem down into sub-problems. Yeah. Now, don't get me wrong. I'm not trying to diminish the effect of the work or anything else like that. Just from a very high level, it may be worthwhile just thinking about the fact that the behavior-based people have been basically doing this task decomposition. Very simple control laws, extremely simple robots. That's the game. You couldn't do this with a behavior-based system. I mean, these behavior-based systems just don't scale when it comes to degrees of freedom. It's as simple as that. But you might want to say something to the effect of, I don't know, saying to think about it, that the finite state machine architectures for how you program these things when it comes to behaviors. You have this current state you're in, approach the object, whatever else. You basically, each state provides the funnel into the next state such that it provides the initial conditions required for that next state to solve its small, isolated part of the task. Right? And so there may be something that you might want to think about in terms of comparing and contrasting, perhaps, or to say, this fits nicely into the framework of behavior-based systems as well, if you were to wrap it this way. There's some sort of analogy to be made. So that, because you keep referring to these sense, or the plan, or sense, plan, act loop, and say, well, this is old-fashioned. Rod Brooks was saying that in 1980, right? So
But people still use it, and it's still effective.
Right. It has its utility, but it's worthwhile, I think, acknowledging that whole split when Brooks and Minsky separated back in the early 80s. One was very symbolic, and the other was just everything. The world is its own best model sort of thing. Off we went. And they've been thinking about that, but they haven't really been able to do things like this ever before. Those robots. Ian Horswell, who's a graduate student of Rod Brooks, did pick up the lab, find the Coke cans, toss it in the trash can with a mobile manipulator in the mid-80s, because it was very simple. He had a color camera, would visually servo to it, and it was this behavior-based thing. It was suboptimal and noisy as hell, but it more or less did the task very simply, with a set environment just so. And so, I think it just may be worthwhile considering that when you start your paragraphs about the Sense Plan Act, is that that's not the state of the art. Yes, it's used maybe more in the manipulation community where you sense, get your plan, and then blindly grab or something like that. There, it definitely makes a big difference how this differentiates us from that sort of thing. But from the other camp that's been happily doing things for the past 30 years now, or whatever else, just not nearly as complex, right? There's a philosophical issue there. So, I mean, I guess that's not much of a question. It's more of a statement, since it's just us now in the room. We can kind of get into more details here. But that was just a feeling that I kept on getting as I read the thesis, saying, well, look, there's the behavior-based people, and it's very clear where you're coming from. As a manipulation area, rather than this, we're happy to be suboptimal, and we love noise, we bump off the walls, whatever else, this is good stuff, we just embrace it. Community is very different.
Right, and basically there's two extremes here.
Right.
And this is coming from one of the extremes. And you have very good background on the other extreme. Right. And sort of this merging point of where, how you would use these components in one system, and how you should definitely acknowledge that.
Acknowledge that maybe you're starting to blur the lines now. Yeah. This very well could be part of a larger state thing. This is 2 states, 20 states. Yeah. And you could actually go to, instead of robot object, to the store to go do your shopping now, because you have the other states that can do that.
Well, so I mean, I think this is very useful stuff. As a way, potentially in the intro, if you want to tie in that work, I actually have a different view on it, though, because I think, behavior-based things are doing sense plan act, just at a smaller time scale, and a plan might be just a mapping from observations to action.
Right.
So everything does sense plan act, and it does it at different time scales, and there might be hierarchical sense plan act happening.
That's very true.
So for me, like behavior-based robotics, it's essentially still doing sense plan act. I mean, every computer program basically does that in some way.
That's true.
So like from my point of view, like you can say that now the complexity that you can do in this loop is getting larger because computers are so fast now. The planning can be done in real time, and your control loop, of the whole task itself now can be subdivided, in these different ways, and you have these funnels of states arranged. But yeah, I mean, I think it's totally fine if in your thesis, if you want to say that, like you say, you didn't want to confuse people by saying this is not strips planning or that you're specifically dealing with here, but your framework can easily basically be wrapped around at the next level of an abstract sort of AI-based.
I mean, I think it's like that for most. Yes. I guess when you look at from behavioral point of view, the robotics, they really care about how specific modules, how one goes into another. You have these dependencies, the flow of the execution process, and then each one module decides on where to go next, etc. What I was arguing with, at least trying to argue with some of the visibility stuff is you always need this division wherever it occurs. Yes, somebody's going to be calling this, and in the end, when this finishes, your higher level process will continue on. But when you want to grasp something robustly, you need the two together. Yeah, or at least that was the message I wanted. Everything else, yes, it should be. Hopefully, everything is reusable. I think that's the goal of. Yeah, that's the goal of every software engineer.
I have a different idea too. Maybe I shouldn't step in here because then we'll have to be talking about.
That's right.
Well, I mean, this is one of the reasons why, sort of, I did like. In the end, I just want to acknowledge that this work exists, but not go into it because you get into these philosophical discussions.
Which is fine. I mean, it's perfectly fine. I think you take a philosophical stance. This is my philosophy. Here's my thesis. I acknowledge these other philosophies. They may be wrong, but whatever, right?
Right, and then you get
but yeah,
a lot of
it's your thesis, and you make the statement that you want to make. Anyway, so without belaboring that point, but I think it's worthwhile at least you thinking about in the intro or something about what we want to do with that. I wanted to just also ask you about the planning, the perception planning, where you stick your camera. Because the other body of work that I was thinking of a great deal when I saw that was the tracking community. So there you've got a target, you're trying to track, a lot of noise, and you've got uncertainties, and you've got, thinking all about the information filters, component filters, where you act in active tracking, where the shape of your uncertainty matrix, or your covariance matrix, for instance, would then determine where you want to aim your sensor to reduce that uncertainty. And when I was reading that section, I just didn't get a really good sense that you were acknowledging as much of the noise as I think probably is in this. And then I don't know whether it was because the problem that you were looking at was such that the noise was negligible, such that it fit within the tolerances of your system.
Oh, okay. I see where you're coming from. So the visual survey systems that you're discussing, in the way I see it, they fit into the second stage.
Exactly.
You already have the object in the sensors, and now you're concerned with getting closer to it while tracking it.
Right.
So that because maybe something can change in the scene, there's dynamics. Maybe the object can move itself.
Right.
And you want to compensate for it, which is why people do visual surveying. And in the end, you always want the object as accurate as possible. That's why even when you get really close, you track it.
Right.
The stance that I'm coming from is we make just one measurement that's really good, and we try really hard for that. And this involves the planning part. You cannot do that visual surveying. Yeah, that's phase one.
Right.
That you cannot do that visual surveying stuff there. This will get you to a location where the sensor is now observing the target. And then you can do this visual surveying stuff.
Now, when you
Or
say
you
visual
can do-
surveying, I mean, I see you're definitely talking about the gripping and the actual grasp part. But I mean, once again, coming from my side, where we did a lot of just ground robots without arms on them, visual surveying meant anything where you have a sensor and you're aiming your bow and then it's feeding into the control system. So the first part, you're visually surveying to the object because you're planning to it, which maybe isn't exactly
So if you're tracking an object,
visually surveying.
and you need to react very fast to the object behavior, then you would definitely need this. You cannot not need it.
Right.
The task I'm assuming that I'm tackling, the object is static. So as you can see, this sort of removes the need of really doing visual surveying.
Sure.
In the end, you just need one good estimate of the object, and you know it's not going to move. At least that's the assumption that I make, which is not valid all the time. But for robotics application, for factory industrial applications, it is valid. For real-world autonomous vehicle stuff, or maybe you're tracking people, or maybe you're trying to fetch something that moves.
This is actually a perfect example of kind of what I meant by different timescales. So for me, a visual servo is I compute some gradient, right? And that's how I move. And it's a very, very tight closed loop, so the time scale is small.
Mm-hmm. Right.
Here, you're actually doing a plan. Like, you're actually searching the configuration space and then moving. But you could always, you could basically move a little bit and replan. So, you could change the time scale at which you do this and actually do a kind of gradient following if you wanted to. But, the question is how complicated is sort of your mapping from your observation and how you convert that into an actuation pattern.
Right.
And so, for me, okay, you could either just, compute a little image gradient and then, map that to, some motion of your robot and have it run really, really fast. Or you could do this, more complicated planning and have that at different time scales.
Yeah. I think it's worth mentioning.
So, I mean, it's a kind
there's
of
these types of problems that people might be interested in.
Yeah, just kind of putting yourself into the framework of a larger picture.
Yeah.
Which is actually, that's my first question about how accurately can you guess the initial pose of the object from when you start came from. Because for me, like Robocop or whatever else, the IBO barely sees the world and barely understands, and all we can do is just head in a rough direction and hope we get more information. It's extremely noisy.
Yeah.
And so, So that's kind of where it came from. Is well, if you know that there's an object there, but you have absolutely no idea what the orientation is, that changes things a lot. And so you might try going this way, you might try going that way. Actions that were even planning purposes for explicitly trying to reduce the uncertainty. You test a hypothesis and you get more information. You revise a hypothesis, plan a new plan. Hopefully get more information. Maybe it works, maybe it doesn't. But each time you do it, you learn more information. Which is maybe step 0.
Then you have to start considering negative information also. And then
exactly. So that's this whole body of work is where I was coming from basically. Is kind of how you might want to say the larger problem is here, and this solves this very complex component of that.
So I guess the way I've structured the thesis, I would like all that context building and previous work stuff and very interesting problem sets to be put in chapter 2. And then the rest of the chapters, not to, I guess, acknowledge so much as to really focus on the problem solved, but really focus on the research papers, use similar research papers that have similar solutions.
I think it's perfectly fine. I think the intro section is where you set the stage, and that's exactly where you would do it.
Okay.
I mean, one thing that I didn't see very pronounced, and it's just fine, was a chapter that is related work. You kind of integrate it throughout, which makes sense, right? But you might do exactly as you say, and just make chapter 2 a little bit more of the related work, saying here's these other areas of study. There's plenty of papers out there for that kind of thing. And if you need references, I can certainly help you from my background is to give you a bunch.
Oh, excellent.
Because you want to get out of here quickly. But at least that sets the expectations of what's coming up, where it lies within everything, and then that's it.
Okay.
Then you just talk about what you know.
Okay. So
I have to go give an immigration talk at 1:55 or thereabouts.
1:55.
Right.
Okay. Then
I have a few minutes, and so
here.
I mean, we can.
Jeremy, do you have any question?
He's
You are the representative of all the audience.
right.
I know.
I'm living with Rosen in the lab downstairs.
Okay.
So we could talk.
All right, then I think Professor Kara, we should have a caucus among the committee members.
Which means I have to get out of here.
Okay, so you two go out.
Okay.